So do you guys remember the trig functions? That was some face. So the trig functions, we're going to start with just two that I'm going to give you. So sine of x, the derivative of sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. So hang on, I'm going to write trig derivatives over here, and we're going to eventually have the derivatives of all of the trig functions. But first, we're going to find the derivative of tangent all on our own. So I'm just going to leave some space here. The other trig functions we have are tangent of x, cosecant of x, secant of x, and cotangent of x. So we also have some trig identities that are going to be useful. Maybe you guys remember some of them. We have two different types of identities that you're going to have to eventually memorize, and those are the Pythagorean identities and they say that sine squared x plus cosine squared x is equal to 1, and tangent squared x plus 1 is equal to secant squared x. Then we have the reciprocal identities, and these are going to be the most important. And the reciprocal identities tell me that sine of x is equal to 1 over cosecant x, or in other words, that cosecant x is equal to 1 over sine x. Do you guys remember these things? Now that I'm writing them down, is it like vague memories, or are you all just like, I've never seen this before in my life? Never. Oh man. Vague, never. Oh, that's bad. Okay. Well, the main thing that's going to be important is the derivatives, and that's all entirely new anyway. So these reciprocal identities we're going to use to find some of the derivatives, but then as we need them more and more, I will keep referring back to them and hopefully help you to remember them. So basically the idea is that there's just this relationship between trig functions. So like each of the trig functions can be written in terms of other trig functions, and sine and cosecant kind of go together, and cosine and secant go together. So cosine is equal to 1 over secant, and secant x is equal to 1 over cosine x. So I'm guessing that some of you have also only ever heard the trig function said in French. Yes. Do the English words translate for you? You don't know. Okay. I also think that maybe sometimes in French school, they actually write out the whole thing. So like cosine as opposed to just writing cos. I'm going to do my best to try to go through this like slowly enough so that you can get used to the terminology that I'm using when we talk about trig functions. The next thing is that tangent x is equal to 1 over cotangent x is equal to sine x over cosine x. And cotangent x is equal to 1 over tangent x is equal to cosine x over sine x. Okay, so since this is new for a lot of you, I'm actually just going to give you most of the trig functions. I think that's easier than trying to derive them when we're all uncomfortable with the identities. So what we're going to do, we're going to just start off by finding the derivative of tangent, and then I'll just give you the rest of them. So normally we would use the identities to derive them, but I think that might just confuse you guys. So we're going to find the derivative of f of x is equal to tangent x. And in order to do this, if we want to only use things that we know and that I've given you today, a good place to start would be by using this reciprocal identity that tells us that tangent is equal to sine of x over cosine of x. So we're going to start off in the same way that we use algebra to simplify. We're going to use these trig identities to simplify. So I can say that f of x is equal to tangent x is equal to sine x over cosine x. Now I have given you the derivative of both sine and cosine. What rule am I going to need to use to do the derivative of sine over cosine? Our options are product rule, quotient rule, chain rule, none. Good job, Miguel. Good job. We're going to be using a quotient rule here. And we're going to be able to do it because I've already given you the derivatives of sine and cosine. So f prime of x is the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. So I want you guys to notice with trig functions, and we're going to really going to be going back and forth between them. But with trig functions, we typically write the power in the middle like that. So in other words, cosine of x squared is equal to cosine squared of x. The reason for that is actually just so that to avoid confusion, because there's a difference between this and this. So if I write this power at the end, if I just write that, the cosine x squared, there could be confusion about whether that power of 2 goes with the x or with the cosine. So if I put parentheses here, these two things are not the same. So cosine of x squared versus cosine of x squared are two different things. And putting that power in the middle helps us to avoid confusion about which one we're talking about. Does that make sense? Okay, so now we're going to use the derivatives that I gave you guys. We said the derivative of sine is cosine. So I have cosine x times cosine x minus sine x. We said the derivative of cosine is negative sine x divided by cosine squared x. So here the derivatives I took are just the ones that I gave you at the beginning of class right there. So in this case, those minuses cancel out with each other and become pluses. And this is cosine squared x plus sine squared x over cosine squared x. Any questions so far about how I've gone through these steps? Okay, can I cancel out those two cosines? Like, can I do that? So I have some yeses and some nos. Are we allowed to cancel when we have a plus sign? No. So I cannot cancel those out because of the plus sign. So instead, I'm going to resort to my identities. What did we say cosine squared of x plus sine squared of x is equal to? Good job, Denny. So our identity says sine squared plus cosine squared is equal to 1. So this right here is equal to 1 over cosine squared x. And this right here is just my Pythagorean identity that we reminded ourselves of earlier. Pythagorean identity. What was 1 over cosine equal to? Oops. I should have an S. What was 1 over cosine equal to in our reciprocal identities? You got it. It was equal to it was equal to secant. So this is equal to secant squared x. So we use our reciprocal identity now. And the answer is that the derivative of tangent is secant squared. And we were able to find that by using a mixture of the quotient rule and the trig identities. So I'm going to go fill that in up here. We'll go back down in just a second. Okay, so the rest of them, I could go through and I could do similar things, but I think that because these identities are new for you, it's going to be easier for me to just give these to you. So the derivative of cosecant is negative cosecant x cotangent x. The derivative of secant is secant x tangent x. And the derivative of cotangent is negative cosecant squared x. Let's see. There we go. All right, now it's all there. Okay. So are there any questions about how I found the derivative of tangent by using the quotient rule? Okay, so you guys are gonna have to memorize these things. So hang on, I'm gonna zoom back in. Come on. So I'm just gonna give you some tips for memorizing them. You can, whatever way you find to memorize, that's good. But the answer is yes, you have to memorize all of these. So it's good to have some kind of trick for helping you memorize them. So the first thing I'm gonna point out, I'm gonna ignore the sine and cosine. I'm just gonna kind of separate those away. You just need to know those. Tangent and secant kind of go together, and cosecant and cotangent kind of go together. So you'll see that they kind of mimic each other. The cos are always negative. So if there's a co, and that same with cosine, tells me that it's going to be negative. No co tells me it's going to be positive. So that's kind of helpful. Yeah, I know, it's a lot, guys. So another thing that I've heard a lot to help memorize this is this mnemonic device like you're whispering to yourself. So again, if you think this is stupid, then pretend it didn't happen. But if it's helpful to you, awesome. It's good to have something to help you memorize. So one thing that I've heard a lot is whispering to yourself. So you whisper to yourself, you're like, psst. So you're gonna write that down. And then what I can see is the SST tells me that the integral of secant is secant tangent. So the S goes with ST, the integral of secant, the derivative of secant is secant tangent, but it also goes backwards. The derivative of tangent is secant squared. And so that helps you to memorize the tangent and the secant. And if you have tangent and secant, cotangent and cosecant just mimics that. So it's kind of a way of memorizing all four of these things. Maybe it's going to be helpful for you. Maybe it's not. If not, forget it, find something else. But you are going to have to memorize all of these things. Okay. So with that said, good luck. Let's do some derivatives. Now ready? So we're going to start off by just doing a couple that only involve the product rule and the quotient rule. And then we're going to throw in the chain rule with trig. Okay, what rule do I need for here? You got it. That's going to be my product rule. That's my F. That's my G. So F prime of X, I'm just going to immediately apply the product rule. PR is sine X plus 2 prime times secant X plus X plus sine X plus 2 times secant X plus X prime. And now I just do the derivatives of each of these things. So the derivative of sine X plus 2 is just cosine X. And then we have plus sine X plus 2. And if we remember our whispering to ourselves, the derivative of secant is secant tangent. So this is secant X tangent X plus 1. And that's my final answer. And so this was really just the same as the type of thing that we've been working on up until now. So we're just going to do one more before we throw in the chain rule. So I'm going to need a quotient rule here. I have a function over a function that tells me I need a quotient rule. So we're just going to apply that quotient rule. The derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. And then this just requires us to know our derivatives. So g prime of x, log base 6, I know that's 1 over x ln 6. Hopefully you guys also know that. You've all memorized that by now, right? That means yes. We're just going to pretend you guys are all like, yes, I know that. Then cosecant x, that's one I gave you today, is negative cosecant x cotangent x. Remember, that's the one that mimics the secant tangent. So that's the derivative of the top times the bottom minus the top times the derivative of the bottom. Again, we can use our whispering to ourselves. Psst. The derivative of tangent is ss secant squared. And derivative of cosine is just negative sine. So again, these are things that you guys need to get on memorizing. And that's your final answer. Are there any questions about how we can see trig show up in the product rule and the quotient rule? Then this brings us to where derivatives go crazy. And that is when we throw trig into the chain rule. So having trig just makes the chain rule a little bit insane. So we're going to have this whole section for the rest of class called trig and the chain rule. Ah, what happened to my line there? Hello. So the first thing is that trig can show up in the chain rule that we already have. So the first thing is to identify which version of the chain rule we're using. So I'm just going to remind us of the three different things that we've seen. We saw when we have e to a function, we saw when we have log of a function, and when we have a function to a power. So which one of these three things is going on here? Which of these is the first rule that I'm going to need to use to evaluate this? 1, 2, or 3? Exactly, I have a function to a power. Just so happens that that function is a log, but it's still a function to a power. So it's actually this one. I have my g to the power of 9. So when I do my derivative here, f prime of x, I bring the 9 down. I don't touch what's inside. I subtract 1, and then I pull out the derivative of the inside. And then with this new derivative, I ask myself, product rule, quotient rule, chain rule, or none? What do you guys think? It's going to be a log chain rule. I have log of a function. So this is log base 8 of secant. This is actually this, is actually this form that we have over here. So this is my log of a chain rule. So this is, like, we could say log base 8 of g. This is another chain rule. So this is a chain rule embedded in a chain rule. So then f prime of x, the stuff I've already written doesn't change. But now I'm applying my chain rule to the outside. And this chain rule here says the thing inside goes on the bottom with a ln 8. And then on the top, I have the derivative of the thing inside. Now I ask myself again, product rule, quotient rule, chain rule, or none? You got it. None, because now it's just secant of x. So it's just an x there. So anyone remember really quickly off the top of their heads what the derivative of secant is? We have our mnemonic device for that one. We have our derivative of secant. You got it, secant tangent. Good job, guys. So this is 9 log base 8 of secant x all to the power of 8, and then I have secant x tangent x over secant x ln 8. Can I cancel those secants out? I can, because this is all multiplication. There are no pluses or minuses I can cancel. And that's my final answer. Okay, So in this next question, we're going to touch on something that people usually struggle with a lot. And we're going to say that when you have a trig function to a power, we want to start by rewriting it. So an example of this, if I have sine, that is an 8, if I have sine to the 8 of x, so we've seen that that's the notation that we typically use for trig functions, but it can be confusing inside of derivatives. So we're going to rewrite it with parentheses and move that power to the end. And that's sometimes helpful for identifying what the rule that you want to use is. So here I've sine to the 5th x cotangent x. And what we have above is telling us to do is to rewrite this thing before I even think about my derivative, to move that 5 to the end and then write cotangent x, because that's going to help us to identify the rules that I need to use. So with that said, now that I've done this, what rule should I start off with here? Product rule, quotient rule, chain rule, none. You got it. This is a product rule. I have two things being multiplied together. So this is a product rule. Good job, Easton. So then g prime of x is the derivative of the first, so that's sine x to the power of 5 prime times cotangent x plus sine x to the power of 5 times the derivative of cotangent x. So then we're looking at each of these primes, each of these derivatives, and we're asking ourselves again, product rule, quotient rule, chain rule, none. So for sine of x to the power of 5, do I have a product rule, a quotient rule, a chain rule, or none? And it might be helpful to go back and look at the things I have in green there. I'm going to number them just to make our lives easier in terms of asking questions. If it's a chain rule, which one of those three am I using? One, two, or three? What do you guys think? I have an answer from Dean. Good job, guys. It's 3. This is a function, just so happens to be a trig function, but it's a function to a power. So this is like g to the power of 5, and it's a chain rule. Whereas this cotangent, there is no power, this is just none. So this is just the derivative, I can't remember writing none. This is just the derivative as we have it. So now I'm applying my chain rule of g prime of x. I'm applying that g to the 5, so I do 5. I don't touch what's inside. I subtract 1, and then I pull out the derivative of the inside. There's nothing to do here, so I'm going to move that 5 back to the middle. Anyone remember the derivative of cotangent? That's okay. Negative cosecant squared x. So we can also use our here. SST, that tells me the derivative of tangent is secant squared. So the derivative of cotangent is negative because it's a cosecant squared. Then I have one derivative less to take. This is just a known derivative, so I can just write down my answer here. G prime of x is 5 sine to the 4th of x times cosine of x times cotangent of x plus sine to the 5th of x times cosecant squared x. And I'm actually going to take that minus and move it to the middle. And I'm going to highlight that to show we can do that. That minus can just change the sign out front there because it's all multiplication. So it's like there's a multiple of -1 there. So we can just change that sign in that way. Okay, and this is my final answer. Now I could simplify this if I wanted by reusing my reciprocal identities and rewriting cosecant and cotangent, but I'm not going to ask you guys to do that. I'm just going to show you how it would be done in case you want to know, because sometimes it's helpful. So we know that cotangent is cosine x over sine x, and those signs cancel out, and this is actually sine cubed times cosine squared. And then over here, cosecant squared is actually 1 over sine squared. So this is actually just sine cubed x. And that's just another way of rewriting the whole thing in a simpler way. Okay. It's not really that important, but I used my reciprocal identities up here. So I said that I just used these identities that I reminded you guys of at the beginning of class. I know that cotangent is equal to cosine over sine, and I know that cosecant is equal to 1 over sine. So I rewrote my cotangent and my cosecant using these identities right here. So cotangent was cosine over sine, and cosecant was 1 over sine. And then because of that, that cotangent had a sign in the denominator, so I was able to cancel out one of the signs. And the sine to the 5th times cosecant squared became sine to the 5th over sine squared. And so here I was really just applying the rule that if I have a to the n over a to the m, I get a to the n minus m. It just so happens that in this case, my a is sine x. Did that help at all? Don't worry about it too much. I'll be doing it a few more times, and then when it becomes important, we'll focus on it a lot more. But for right now, as long as you can get to that thing in blue, like that's what's the most important. Because I'm okay with you leaving your answer like that. Okay, so again, I have a cosecant cubed. We said the first thing to do when you have a trig function with a power is to rewrite it with the power at the end. So here, do I have a chain rule, product rule, quotient rule, or none? I've got my chain rule. This is like 2 to the g, so this is a chain rule. So then h prime of x, I just apply my rule here. So it doesn't change. I rewrite what I have. I throw in a ln 2, but then I need the derivative of my g. So then I ask myself again, quotient rule, product rule, chain rule, none. Chain, this is again the same thing we had in the last one. This is like a g to the power of 3. It's just that in this case, my g is a trig function. I still need a chain rule. So here I'm going to have h prime of x is equal to 2 to the cosecant of x cubed times ln 2. I bring my 3 down, I don't touch what's inside, I subtract 1, and then I pull out the derivative. And now this is just one of the rules that I gave you guys at the beginning of class today. So the 2 to the cosecant cubed x times ln 2 times 3 cosecant squared x. That cosecant, we were told, is negative cosecant x cotangent x. And that negative I can actually move out to the front so that we don't have confusion, because if you have a negative and you don't write parentheses, it is wrong because you are subtracting, you are supposed to be multiplying. So moving that negative to the front avoids accidental subtraction. So I'm going to move it to the front. I'm going to have the negative here. And then I have my ln 2, and then I have my 3 cosecant cubed of x cotangent x. So here I just also multiplied my cosecants together for my final answer. Okay, are there any questions about what we did right here? Now here, the simplification I did is actually important. So I want to make sure that you guys understand that. In the last question, it wasn't important yet. Don't want you to worry about it too much. And this one, what I did is important. Any questions? Okay. So here we just did 3 questions where we saw trig functions show up in the chain rules that you already know, that we've already learned. But trig functions also have chain rules of their own. So trig functions also have chain rules of their own. So I'm just going to do this with sine to start. So Is this sine times x? Yes or no? Is it sine times x? You don't have to know the answer, but I do want to know what you think. Can I insert the word times between the sine and the x? I only have 2 answers so far. I want to know what you guys are thinking because it's going to help me to know how much I need to talk about it. Okay. So the answer is actually no. This is not sine times x. I am not doing a product rule when I look at this. I'm not multiplying 2 things together, not sine times x, but sine of x. And that distinction is really important because what it tells me is that without this x right here, sine doesn't make sense. And so in the same way that we don't say ln times x, we say ln of x. I don't do a product rule when I see a ln x. I just do 1 over x. Sine is the same. This is sine of x. And what that means is when we're doing a chain rule, if I have something other than x, if I have a whole function, I need to do a chain rule. So in other words, this sine x here, if I have sine x, that's sine of x. The derivative of that, we said, is cosine of x. But if I have sine of a function, then I need to do a chain rule. So I have a function in there, it's sine of a function, then this would be cosine of that function times the derivative of that function. So in other words, if we have anything other than x inside, because it's of x, we have to do a chain rule. So I'm going to do an example that hopefully helps you guys see the difference between like of and times here. And then we're just going to do a bunch of chain rules that have trig inside of them. Actually, I'll call this one g of x. What is the difference between f and g? Am I going to do their derivatives exactly the same way? got it, Usman, exactly that. So if I read this one would be read sine of cosine x. This is sine of x times cosine of x. So here, this is a product rule where that's my f and that's my g, whereas this is a chain rule where the function inside is cosine. Do you guys see the difference between the two things? Let's do the derivatives then. So this one would be a chain rule. So I'm going to say the derivative of sine is cosine. So I do my derivative, I don't touch what's inside, and then I pull out the derivative of the inside. And the derivative of cosine, we said, is negative sine. Remember, cos go with negative. So f prime of x is cosine of cosine x times negative sine x. And I can bring that negative out to the front. And that's my final answer. Over here, though, I'm going to be applying a product rule. You cannot do the cosine squared x here because it's not cosine x times cosine x, it's cosine of cosine x. So it's not the same thing as cosine x cosine x. So this does not equal cosine x cosine of x squared. It is cosine of cosine x, and there's a difference between the two things. You guys see that distinction here? Okay, so now I'm gonna be doing my product rule. So I'm just applying the derivatives that I told you guys. The derivative of sine x is cosine x, plus sine x, the derivative of cosine x is negative sine x. Why did I put a cosine at the beginning of f prime of x? Because the derivative of sine is cosine. So here I had my sine, the derivative of sine was cosine. So it's cosine of cosine x. And when we look at this up here, we said to do the derivative of sine of g, I do cosine of g times g prime. So the sine actually kind of becomes a cosine when I do the derivative. Does that make sense? Okay, what about over here? Can I do cosine squared x over here with my g prime? I couldn't with my f prime. Can I do it with my g prime? Yes, because it's cosine x times cosine x in this case. It's not cosine of cosine x. So this one I actually can rewrite as cosine squared x minus sine squared x. So they both have x's over on the right, they don't over on the left over here. Oops. And this is why people love trig. All right. Are you guys ready to do more trig derivatives with the chain rule inside the trig? It's intense. It gets crazy. So I'm just going to start over. Let's say that I have f of x is equal to secant of the square root of x plus 9x plus 9 to the x. So is this secant of x or is it secant of a whole function? It's a whole function, so that tells me that I need a chain rule. That's my g, I need a chain rule. So to do this, we're saying I do the trig derivative. Who remembers what the derivative of secant was? We can whisper to ourselves if we need to. The derivative of secant is, so what comes after the s? You got it, secant tangent. So what that means is I'm doing secant tangent of this same function. So f prime of x is equal to secant of the function times tangent of the function times the derivative of the function. So this is like secant g tangent g prime. So I do my derivative as normal, and I pull the inside function to the outside, like fruit roll, if I'm just pulling it out. So then f prime of x here is equal to secant of the square root of x plus 9x plus 9 to the x tangent of the square root of x plus 9x plus 9 to the x times, I will answer that question after I finish writing the answer. I think I understand your question. So now I'm just doing the derivative of this thing. And these are all just simple, straightforward derivatives. This is my final answer. Okay. Oh crap, hang on 2 seconds, guys. Okay, sorry about that. Okay, so the question that I have here is why didn't I write secant and tangent in front? And the answer is it goes back to this of idea. This is not secant tangent x. When I look at my derivative here, if I look at the derivative of secant x, I get secant x tangent x. Is that the same thing as secant tangent x? Are these two things the same that I wrote? No. This would be secant x times tangent x, and this would be secant of tangent x. There is nothing there, so that x isn't there, so secant is being evaluated at tangent x in this one. So in the same way, if I have an x, if I have a function instead of an x, here I have secant of g, the derivative, I have to evaluate that secant somewhere, so it's going to get evaluated at the function. I have a function instead of an x, so where I would have had an x over in my derivative over there, I'm going to have an x in my derivative over here, which is not equal to, so actually let's write this as like an x right here, which is not the same thing as saying secant tangent g times g prime. This would be secant of tangent g, but the derivative tells me times, not of. Nick, does that answer your question? Okay, so let's do another one. I think we have time for a few more before class is over. Okay, what did I say the first thing to do when you have a power is? Have a power, what should I do? I'm going to rewrite it. I'm going to move that power to the end. So I'm going to write this as cotangent of x squared plus 2 all to the power of 2. And so I can see here that my main rule is the fact that I have a g squared here. I have a thing to the power of 2. So when I do g prime of x, the first chain rule that I'm going to apply, I'm going to bring the 2 down. I'm not going to touch what's inside. I subtract 1. So my new power is a 1. And then I pull out the inside function as a derivative. Okay, now here I have cotangent not of x, but of a whole function. So now my inside function here is that x squared plus 2, and I have another chain rule that I need to do, but this time it's that trig version of the chain rule. So I'm going to write 2 cotangent of x squared plus 2 times the derivative of cotangent we said was negative cosecant squared of x squared plus 2. So it's being evaluated in the same place as that original function, but then I have to pull out my g and multiply by that derivative. Take a second. Do you guys see what I just did there? And now this prime that's left over is just a simple power rule. So I'm going to get that g prime of x is 2 cotangent of x squared plus 2 times negative cosecant squared of x squared plus 2 times 2x. And because this is all multiplication, I can simplify this. So I can move the x and the constant to the front. And that's my final answer. And I want to do one more problem today. Hopefully it won't be too long. Okay, h of x, is it cosine of tangent of x squared or is it cosine times? You got it. That's an of that goes there. So this is a chain rule. And my inside function is that tangent. That's my g. So h prime of x, the derivative of cosine is negative sine. So the cosine gets replaced with negative sine of what? The inside function doesn't change. So it's of tangent of x squared. But then I pull out the inside function and prime it. And now here I have another chain rule where my inside function is that x squared. So now I have tangent of x squared, not of x, but of x squared. So h prime of x is negative sine of tangent of x squared. The derivative of tangent is secant squared. So the tangent gets replaced with secant squared of x squared times the derivative of x squared. And now we are done. The negative sine of tangent of x squared times secant squared of x squared times 2x. And that is my final answer. And now we are done today. And don't worry, trig's not on the midterm. That said, we are going to do one more class on trig before the midterm, and these ideas of these embedded chain rules are on the midterm, just not with trig. So that's all. If you have any questions, I'm happy to answer. Other than that, I'll see some of you tomorrow.